Who can tell me what a relation is? What's the word mean to you in English?
Greater than, less than, equal to.
Yeah, greater than or less than or equal to?
Yeah.
Yeah, that's a relation. Because it connects two different items with some kind of relation, right? If we say that 2 is less than or equal to 3, that's true. Can we say 3 is less than or equal to 2?
No.
No, we could say it, but that would be wrong, wouldn't it? Yeah, so it describes a certain relationship. What about in your family? What about parents and children? Isn't that a relationship? Okay, in English we think of it that way. And we're going to use those types of relations because they're more important to us in the world of computing. When you are storing data and you're looking at the relationship in tables of data, you're going to normally be looking at something other than numbers, aren't you? Or at least the mathematics of it. Okay? So let's take a look at it. Let's say that we have now, if I put this in a block, like this, separate these, then we might call that a table, right? Now, are there relationships going on there? Yes. For instance, this row is a relation, isn't it? Because it's information about John. So John's related to this street address and to that phone number. And Sally's related to this street address and that phone number, etc., right? Well, we could show this in set formation, or set form this way. Remember we used the squiggle marks for set. And we could say John, comma, 123 Elm Street, comma, 770-325, oops, 325-7416, comma, Sally, comma, 205 Ashway, comma, 678, etc., etc. And notice what we're doing between the relations, we're separating these using these marks here rather than parentheses or anything else. And that's really a convention to tell us this is a relation. Okay? Does that make sense? All right, now, that's what you may see when you're working with data and databases. To work with relations now, though, let's make it simpler, and we're going to talk about binary relations. Everything we're talking about in binary relations apply to n-tary, as they call it, any length. These are tertiary. There are three things per relation. A binary, what would binary be? How many? Two, right? Because everything we've been doing is binary, isn't it? So, I could have a relationship, and I could call it parent-child, and I could have Bob, comma, Bill, but I could have Bob again, couldn't I? Because probably, if Bob is a father, he might have more than one child. And so forth. Let's see, Mary and so forth. And that would be a relationship of parent-child. The first one being the parent, and the second one, the child. Okay? Is that a relation? It is, isn't it? Probably the best way to show it's a relation is to go ahead and write it the way we would if we're going to graph it, right? Instead of f of x, we want to put y there, right? So what is that a relationship of? It's a relationship of x's and y's, is it not? So if I put down 2 for the x, then it's going to be 2 times 4, right? Which is 8 plus 7 is 15. And if I put 3, that's 2 times 9, which is 18, plus 7 is 45, is that right? Etc. Okay? Okay? Does everybody see how that works? So relation, we learned in math, you should have learned that one over there. Functions are a kind of relation, and we're going to deal with that more next week. So when we're talking about things like relations and functions, don't get the idea they're two diametrically different things. There are things called relations. Within that, there's something else called functions, and we'll deal with that more next week. Okay? So let's talk about some of the properties of relations that we're going to want to deal with. And the first one I want to talk about is reflexive. Now, the reflexive property of a relation, by the way, these are properties of the whole relation, not just of some of the entities within the relation. So unless everything applies to this, the relation is not reflexive. So what this says is, if A is in the relation, then AA is in the relation. Okay? In other words, every element that's in there is related to itself. Okay. What's a relation that might be that way?
1?
Hmm?
Good. I put 1.
How about equals? Would equals work? If 2 is in the relation, isn't 2 in the relation? Isn't 2 related to itself by equals because it's equal to itself? Did I see that? Okay. Then we have symmetric. And symmetric says if A and B are, let's see, let's put it this way. If AB is in the relation, then BA is in the relation. Or in other words, I can turn every one of them around. Well, equals would be another example of that, right? If A is equal to B, isn't B equal to A? Okay. We also have something called anti-symmetric. And that says that if AB is in the relation, then BA is not in the relation. Okay, so it's the opposite. And lastly, we're going to talk about is transitive. And transitive says if you have AB and BC in the relation, then AC is in the relation. And notice this is now three different things. We have A, B, and C going on. And what it says is that if A is related to B and B is related to C, then A is related to C. So you should always look at it this way. A is related to B. There's a link of the B to the B. B is related to C. And the first is related to the third. Now those are the properties that we're going to be looking at when we talk about relations. So let's put some relations up here and see how they are defined here. Let's look at parent-child. Is that reflexive? No. Because what would reflexive mean? Each parent is their own parent? Or each child is, but we normally start with the first one. So, yeah, but same idea, wouldn't it? But each parent is their own parent, right? So it's not reflexive. Is it symmetric? What would it mean to be symmetric? That a parent who has a child is also the child of that parent, of that? No, you can't go backwards, can you? Okay. Is it anti-symmetric?
Yep.
Very good. It is anti-symmetric, isn't it? Is it transitive?
Wait.
No, let's talk about grandparents.
Good. There's where the discussion comes up. You already said that if you're talking about grandparents. And for our purposes, and you're going to see this when we start studying trees, parents are only the immediate parent of the child. When you go further up, you're talking about something else. Okay? So it is not transitive. Okay? I have children who have children. I am not their parent. I'm their grandparent. Okay? So, anti-symmetric, that's all it is. Parent-child is anti-symmetric. Let's see if we can get one that goes further than that. Let's talk about less than or equal to. Is that reflexive?
Yes.
Every number is less than or equal to itself, isn't it? Because it's the equal side. So yeah, it's reflexive, isn't it? Is it symmetric? Yeah, and there's where I want to see, how do you see this? It can be, right? Sometimes it is. But remember what I said about these properties. These properties are properties of the whole relation. So in order for them to be a property, it must always be. So now, is it symmetric? No. Okay. Because 5 is less than or equal to 8. but 8 is not less than or equal to 5, right? So therefore, it's not symmetric. Therefore, is it anti-symmetric?
No.
Very good. All right, now, this is one of the biggest problems we run into. Notice what they said. We said it's not symmetric, but now we just found out it's not anti-symmetric either, is it? And it's because you've got a gray area between symmetry and anti-symmetry. Symmetry says always you can turn them around. Anti-symmetry says never can you turn them around. Okay? Therefore, it is neither symmetric nor anti-symmetric. Is it transitive? It is, isn't it? If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C, right? So it is transitive. How about this one? Relationship brother. Is brother reflexive?
Yeah. Well, no, because a brother can't be a brother to itself.
Exactly. And in fact, the best way to say that is, if you were only child and somebody said, do you have a brother? You'd say no, right? Okay. So it's not reflexive. Is it symmetric?
No. You could have a sister.
Very good, you caught it. Let's say that a girl has a brother. Does that brother have a brother? No, that brother has a sister. So it's not symmetric. Is it anti-symmetric?
No.
No, because sometimes it is two guys, right? And they're brothers. Let's see, what about transitive?
Yes.
Yes, it is. And it doesn't matter if the first is a girl. If she has a brother, and that brother has a brother, then that second brother is her brother. Okay? So it's transitive. And that's all it is, isn't it? It is just transitive. So you begin to see how these work? It's just the concept of relation. It is going to affect when you start building tables in databases. You want to think about some of these things as you start designing how you want that to happen. Okay. Okay, let's okay. Looking at that set, that relation, is it reflexive? Who thinks this might be reflexive? Notice that I have AA, don't I? But B is in here, and I don't have a BB, do I? I don't have a CC, and I don't have a BD. And it has to be a property of the whole thing for it to be in existence. So it's not reflexive, is it? Is it symmetric? What you do is you go right through. It's like, if AB is here, then to be symmetric, I'd have to have BA, wouldn't I? And right away, I don't have that. Well, let's see. Is it anti-symmetric? Let's see. I don't have BA, so that's good. Do I have CB? No. Do I have DA? Now, this one might be confusing because you'd say, well, gee, AA and AA, right? But when we talk about symmetry, what we're talking about is that the A and B are different values, okay? They can't be the same. Otherwise, every reflexive would be symmetric, right? So, that's not antisymmetric either. Is it transitive?
Yes.
It is. Where's the transitivity?
A and B.
We've got AB,
BC.
we have BC. Do we have AC? Remember, to be transitive, and that's good that you saw the first two pair. When you have the first two pair, you must also have the first and the last. So, it's not transitive, but you're heading towards what I want to show you. Is there any other close opportunity for symmetry there? There isn't, is there? The only opportunity is these are the first two pair in a transitive string. Yes?
Could you explain one more time why it's not antisymmetric?
Well, it's not antisymmetric? I'm sorry, it is antisymmetric. You're right, it is antisymmetric. Yeah. That's what I was trying to say. This doesn't fulfill that. So yes, it is antisymmetric. Because none of them are in reverse. Yes. Now, what we see is that we have an opportunity for transitivity, but it's not fulfilled. So there is a concept called transitive closure. And what transitive closure means, it's the smallest set that then makes that transitive. All right? There are a lot of things I could do and make it real long and add lots of stuff. But what's the minimum that I can do to make that transitive? Well, what I see is that this pair and this pair are the only items in here that begin a transitivity. So what I need to do is add the third one. Yes?
Can you only have a transitive property with things that are in like a set order? Like we're using letters here that have a set order like that. You could do it with like 1, 2, and 3. Like
Yeah.
1 and 2 are in it, 2 and 3 are in it.
Right.
1 and 3 have to be in it.
And they don't have to be in order, but they have to be ordered within their pair, because we call these ordered pairs. Yeah. So to do transitive closure here, what I would do is I would have AB, AA, BC, and AD, the original ones, so that's the original set, and then I would add AC. Now, that set is transitive.
So with transitive, you don't have to have it for every single thing in the set.
Only when you have the
Just
first
have
two
to have it.
elements. So it's an if statement that needs this to get started. And that's the hardest thing for transitivity for most people. If you have these two, then to make it transitive, you have to have the first and the last in a pair. Okay? Any questions on that one? That's the concept of transitive closure. Okay. Now there are the other closures, but we don't really consider those. The transitive closure is the only one that's really important to us. Okay. So, really what that gets into then is what we call partial orders. Now, partial orders are sets that are reflexive, transitive, and anti-symmetric. And the best example of this is if you're in the line at a checkout counter, like at Walmart. That line is a partial order. Okay? You are where you are in the place in the line, right? So that makes it reflexive. Everybody is where they are. If there's somebody behind you and then somebody behind them, isn't that second person also behind you?
Yeah.
Okay? So there's a chain, isn't there? If somebody's behind you, can you also be behind them? No. Okay. So the line at Walmart is a good example of what it means to be a partial order. Okay? And we'll see those in sets as well. Okay. So let's look at some examples. Okay, so this is actually going to be your quiz for this week. But let's go ahead and start it in class together and see if we can't get some of these ideas to make sense. So, which of the following properties holds for the relationship sibling? All right, now sibling is a little different than the brother-brother thing we talked about a little while ago, right? Yes.
The quiz isn't active.
I'm sorry?
The quiz isn't active.
I know, it's going to be active Wednesday. Okay, and I'll probably move it up as we get far enough along today. Yep. So, what about sibling?
It would be symmetric as long as we're not including parents.
Transitive and symmetric.
So we would say it's symmetric? Okay.
Transitive.
Is it transitive? Yeah. Is it reflexive?
No.
No. Right. Because if you are a single child and somebody says, do you have any siblings, your answer is no, right?
Yeah. So,
That's the best way to answer some of these is go through it in your mind and ask yourself how you do it. And it's not anti-symmetric, is it? Okay. All right. Some of these beginning to make some sense? Okay, so here is the one we did with parent, right? So did we say that parent was what?
Anti-symmetric.
Just
Anti-symmetric, isn't it? It's not symmetric because your child can't be your parent. And it's not reflexive because you're not your own parent. Right? And if you, let's see, if you are a parent of a child and that child has a child, you're not the parent of that child, you're the grandparent. So, anti-symmetric is the answer for that. By the way, notice this is one of those quizzes where you check all that it can apply. There's not one right answer. Okay. What about sister? Is sister reflexive?
No.
Is sister transitive?
Yes.
It is, right? Because if you had a sister, and your sister has a sister, then that sister is also your sister. It doesn't matter whether you are a boy or a girl to start with. It has nothing to do with the first one, does it?
No.
Is it symmetric?
No.
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 The reason I chose brother is because we have mostly guys in this room. And when they did this one first, before, it was too obvious. So sorry, ladies, I did it the other way to try to get people to see what was going on. But yeah, this is the one that's on the quiz. And you're at a disadvantage now because when you see this, you say, if I had a sister, well, of course I'm their sister, right? But no, that wouldn't work for everybody in the relation because you could be brother. Okay, so it's not symmetric. Is it anti-symmetric?
No.
No, because sometimes you do have a sister-sister relationship, which are reversed. So the only thing here is transitive. Okay? What about the empty set? Is it reflexive?
Is it reflective?
Is it reflexive? It is, isn't it? Because notice that all of the definitions were if statements. If A is in the set, then AA is in the set. Is A in the set?
No.
No. What happens when the first part of a if statement is false?
True.
The if statement's true, right? So it is reflexive. What about transitive? Yeah, it's transitive. What about symmetric?
Yeah.
Yeah, it's symmetric. What about anti-symmetric? Yeah, this is one case, it's kind of funny. How can you be symmetric and anti-symmetric at the same time?
Because of them.
Well, it's because of the definition of the if statement. I hope we all got that from when we studied logic. Is everybody okay with this? Well, you not be okay, it's kind of strange, isn't it? But okay in understanding it, right? Okay. What about this one?
Just reflexive.
Is it reflexive? It is, isn't it? Is it transitive?
No.
Well, what's transitive say? If AB and BC are in the set, then AC must be in the set.
But first part's false, so I guess.
First part's false, therefore
It is transitive.
it's
It
true.
is-
That's why I want to do this in class. Is it symmetric? It is. It's not symmetric because AA it can be reversed. That's not why it's symmetric. It's symmetric because there is no AB. All right? So therefore it is symmetric. And it is also anti-symmetric. Okay? So, the empty set and this one are both everything. They're both examples of everything.
Before you go on, could you just explain the whole transitive thing again? Is it because it's transitive on top of itself?
Yeah, the transitive says, if AB and BC are in the set, are AB and BC in the set? Or anything like it? No. Notice all of these are just related to themselves. So there is no string for us to measure. But the if statement starts with if A, B, and B, C. They're not there though, are they? So that's false. It has nothing to do with actual what's here. It has to do with what's not there. Does that make better sense? Okay. The setup isn't there. And if the setup isn't there, then the first part of the if statement is false. Okay? Okay. Now, what about transitive closure for this set here? Do I have any beginnings of a transitive string?
1, 2, and 1, 3.
1, 2, and 2, 4.
Right.
Oh, right.
Got it? Okay.
Yeah.
And that's very common to see that way. No, wait a minute. Yeah, it's got to be the second one that's got to be the first of something else to create a string. Think of it as linking together, okay? So we have 1, 2, 2, 4. This 1, 3 doesn't really have a pair that goes with it, does it? Okay? So the only beginnings of a transitive string are here and here. Now remember what we did for transitive closure? We add the minimum we needed to now make it transitive. So what do I need to add to this to make it transitive?
1, 4.
1, 4. Everybody see that? It's got to be the first and the last. So it's 1, 4. So here's 1, 2, 1, 3, 2, 4. That's the big what's already there. And here's the 1, 4 added. Now down here, you got 1, 2, 1, 3, 2, 4, 1, 4, and then they added 3, 4.
What?
Yeah. Does that really add anything? Well, we have 1, 3, 3, 4, 1, 4. That's another transitive, isn't it? It's still transitive, but remember by definition, transitive closure is the minimum you need to add. It's nice they added that, but that's not transitive closure. Does that make sense? Okay. Okay. Equivalence relation. Now, an equivalence relation is named after the equal sign. So when we think about equal, is the relationship equal reflexive?
Yes.
Yes, because every number is equal to itself, isn't it? Okay. Is it symmetric? If A is equal to B, is B equal to A? It is, isn't it? Is it transitive? If A is equal to B and B is equal to C, is A equal to C? It is, isn't it? So that's the definition of a reflexive or an equivalence relation. An equivalence relation is a relation that is reflexive, symmetric, and transitive. Okay? So knowing that now, let's look at this. Is this reflexive? This first one?
No.
What's missing?
3, 1.
3, 3. Reflexive is itself. Yeah. 3, 3 is missing here, isn't it? So that's not it. What about this one? We have 1, 1, 2, 2, and we have the 3, 3, right? We have 1, 2. Do we have 2, 1?
No.
It's not symmetric, is it? Here we have the 1, 1, 2, 2, 3, 3. We have 1, 3. Do we have 3, 1? We do, don't we? Do we have a transitive string starting anywhere here? Some people look at 1 to 3, 3 to 1, therefore 1 to 1. That's not transitivity. It has to be 3 different values.
No.
But because there's no beginning to a transitive, is it transitive? It is, because it doesn't fail the transitivity, or the if statement has a false to begin with. So this one really is an equivalence relation. Let's look at this one. We have 1, 1, 2, 2, 3, 3. And here we have 1, 3, but we don't have 3, 1, do we? So if you are good at taking tests, right, and eliminating everything else, this is the only one that works. But this one works because it is reflexive. 1, 1, 2, 2, 3, 3. Everything's related to itself. When we have two different ones that are related, 1 to 3, then we also have its reverse, 3 to 1. So therefore it is symmetric. Transitive says if I have these first two pairs, A to B, B to C, then I'll have A to C. But I don't have the first two pairs anywhere here, so therefore, by the definition of the if statement, it is transitive. Okay? Is everybody seeing that?
So equivalence has to be reflexive, transitive, and symmetric.
That's correct. That's correct. That's the definition of being equivalent. Okay, now what I'm going to do, the last three are total order, and I'm going to wait till Wednesday to talk about total order. It is an extension of partial order, which was the line at Walmart. We're going to talk about total order next time. Do you want me to bring the quiz open and see what you can do?
It's got 3 trials.
Does it have 3? Good. Yeah, if it has 3 trials, why don't you try one by Wednesday? See if you can figure out from the readings what a total order is. All right? Understand that picture of Walmart, okay? There's just one more thing that you need to look at to make it a total order.